Okay, hi, we meet again in my video number 5. This is my video number 5. Okay, in the last video, I think I stopped at the cross product between two vectors a and b, where if you have a vector ab, the cross product a and b, that gives you a vector c which is perpendicular to a and b, a cross b, okay? And such that our vector c is perpendicular to a and c also perpendicular to b. So what can we see from here? If we substitute this c with a cross b, so what we have is a cross b is perpendicular to a. So what we can say from there, a cross b, if you dot with a, that give you 0. Okay, because why? Because they are perpendicular. So the same thing for the vector b. All right, so we have our c is a cross b is perpendicular to b. That give us a cross b dot c, a cross dot b, dot b, that give you 0. Okay, so this come up with a theorem. A cross b is orthogonal or perpendicular to both vector a and b. Yeah. Perpendicular to both vector a and b, which means we have a cross b. This should be a vector a cross vector b dot vector a. This is equal to vector a cross vector b dot vector b, that gives you 0. Okay, next we have another result for the cross product theorem. If theta is angle between a and b, if theta is the angle between vector a and b, and theta is between 0 and pi, then we have a cross b, magnitude of a cross b, this is equal to a b sine theta. Okay, what's the immediate consequences of this formula or this theorem? We can say is that if the two lines or two vectors are parallel, for example AB parallel, so we have a vector A, we have a vector B. This is a vector A, this is say vector B. So we can see from there they are parallel. So when they are parallel, so the angle between them is, we don't have those angles, so that's 0. So that give us A cross B, vector A cross B, this is 0. So to show that any vector are parallel, so you just need to show A cross B, magnitude of A cross B equal to 0. So and for the other case, where to show the vector are perpendicular, we use dot product. Okay, so if you want to show they are perpendicular. This is vector A, this is vector B, so we use dot product. We have seen this earlier, right? We use A dot B that equal to 0. Okay, so how to prove this? How to prove that theorem? Okay, probably there are other ways of proving. So I'll try to prove in the simplest way, but of course simplest way sometimes take a little bit longer because we need to consider each element of A, B, and C. Okay. Now to prove this, theorem, we need to show that the magnitude of A cross B squared, this is equal to A vector unit magnitude of A squared, magnitude of B squared minus A dot B squared. And this is not difficult. If you can show that, then it is not difficult that to show that A squared B squared sine squared, because by definition we have A dot B is magnitude A magnitude B cos theta, and then you factor out we factor out A squared B squared, so what left is 1 minus cos squared, so 1 minus cos squared is sine squared, so end up with that. Okay, now again, to prove that or to show that part here, yeah, we let vector A with component ABC, let vector A with component A1, A2, A3, A1, A2, A3, and vector B with component B1, B2, B3. Okay, so if we perform the cross product between these two vectors, just by we can consider this by definition, then A cross B, that give us A2 B3 minus A3 B2. Oops, sorry. This is for component I. This is for component J. A3 minus A1 B3 A1 B2 minus B1 A2. Okay, so that's a definition of A cross B. Then if we take the magnitude of those, so A cross B, that equal to, so we have A2 B3 minus A3 B2 squared plus A3 B1 minus A1 B3 squared plus A1 B2 minus A2 B1 squared. Okay, just by definition of magnitude of a vectors. So this is the component of A cross B. So magnitude of those that what we have, and also square. This is, we should have squared here. Yeah, without that square, we need square root on the right hand side. Okay, then you can just simplify everything in there. So what you have, I think, and then rearrange those things, simplify and rearrange those things. So what you have, you will find A1 squared B2 squared plus b3 squared, okay, plus a2 squared b1 squared plus b3 squared plus a3 squared b1 squared plus b2 squared, okay, minus 2 a3 b2 b3 plus a1 a3 b1 b3 plus a1 a2 b1 b2. And then you need to rearrange again each of these. If I add, I think I might use something else. No, I don't have. Okay, let's try using this one. If I add, we add a1 squared b1 squared plus a2 squared b2 squared plus a3 squared b3 squared, and then we add up those things, we minus again a1 squared b1 squared plus a2 squared b2 squared plus a3, sorry, this is minus a3 squared b3 squared. So what happened now if we do this? So you can of course factor out a1 squared here, and with this one, so what left is we have b1 squared plus b2 squared plus b3 squared. Alright, as well as this one here, you can factor out a2 squared. So what left is we have b2 here. Now we have b1 squared plus b2 squared plus b3 squared, as well as with this. So for the minus here, you can put in here, and this is, that will give you the outcome of, or the result of a dot b. Now, so if you proceed this, so what we have, I need this thing. So what we have is that this is equal to, we have a1 squared b1 squared plus b2 squared plus b3 squared, plus a2 squared b1 squared plus b2 squared plus b3 squared. Okay, this is from here, from this part here. Yeah, so with this and that, so you can factor out a1 squared. So we have b1 squared b2 squared b3 squared. Okay, done that one. And then with this, okay, we can factor out a2 squared. So what left is we have b2 here, so this is b1 squared plus b2 squared, and so on, as well as b3 a3. So we have for that, and then so, and then this we combine with that. Okay, I hope you can see those things. All right. Okay, so then this gives us a plus, okay, plus a3 squared b1 squared plus b2 squared plus b3 squared. Yeah, minus, we have two, we have minus, minus, we minus this one, this part here, okay, minus that one. So we have minus a1 squared b1 squared minus a2 squared b2 squared minus a3 squared b3 squared, and minus this part here, minus 2 and everything. So we have minus 2 a3 a2 b2 b3 plus a1 a3 b1 b3 plus a1 a2 b1 b2. Okay, then you can rearrange this. Yeah, just play around with the algebra here. So this is equal to, here you can factor out b1 squared, b2 squared, b3 squared. So put it a1 squared, a2 squared, a3 squared. Okay, so we put it that together. So we have a1 squared plus a2 squared plus a3 squared. This one we factor out, so that gives us b1 squared plus b2 squared plus b3 squared. Okay, and for this part, it's basically you can, if you factor out those negative and put the negative out, so you have a1 squared b1 squared plus a2 squared b2 squared plus a3 squared b3 squared plus 2 times of this thing. So we have those three items, and this is another 3 items plus 2, so you have 6 items. So this is basically the minus of a1 b1 plus a2 b2 plus a3 b3 squared. Okay, so from there it is obvious this is magnitude of A, this is magnitude of B, and this is A dot B, this is A dot B, and we have squared that. So that gives us magnitude of A squared magnitude of B squared minus A dot B squared. Then of course from there you can just this give you A squared B squared excuse me. Okay, cos squared theta, you can just factor out those things. That give you A squared B squared 1 minus cos squared theta, and this is sine, that gives you A squared B squared sine squared theta. Okay, so therefore we have A cross B is just, you just take the square root each side, so we have A B sine theta. Okay, so that's the proof of this theorem. And as I mentioned earlier, we have, if A parallel to B, yeah, if A parallel to B, doesn't matter the direction, so what we have is that A cross B, that give you 0. It's not difficult to show that. And if you take the magnitude, even if you take the magnitude, because this will give you the vector, cross product gives you the vector, so we should have those. So in order to have the scalar, so you take the magnitude of those, that give you 0. Now let's look at the application of the cross product a little bit. So let's say application. Okay, if you consider the parallelogram, parallelogram. So parallelogram is the segi empat selari, parallelogram. So we have, let's say we have a vector. This is vector A. Let's say this is our vector A. This is our vector B. Okay, and angle between that is theta, and let's say this, we name it with O. Okay, so of course from there, if we project this point here, let's call this point Q. Okay, if we project this on vector A, so what we have, this is perpendicular to that, so let's call this projection as Q prime. Okay, and then you can move this vector to put there, yeah, so that give you, let's say like that. Then so that basically the parallelogram, so that this gives us the parallelogram. So let's call this point is R. Let's call this point, this is a vector, let's call this point is S. And if we proceed this and project that, so let's call this point as R prime. So that's why for the parallelogram, yeah, what we can find is that the rectangle, that rectangle Q prime, R prime, the area of those rectangle are equal to that parallelogram OQRS. So somehow they must have a relationship between those two vectors, because from these two vectors we can form the parallelogram. Okay, so what we can do, so we can find the area. So before that, let me, so from here we can find that height. Okay, just use a vector B there. So we have vector B, magnitude of B, that sine theta, cosine angle of theta, angle of theta. Okay, so then we can find the area. So area that we mean here is this parallelogram, that area. Okay, is given as, of course we need the length or magnitude of vector A, okay, multiply with the height. Height is given by this. So we have the length of vector A is given as magnitude of A, and then the height of those parallelogram is given as Q prime Q here, yeah, Q prime Q, or Q prime. So where Q prime, this is, we have A, Q prime is B, vector B, sine theta. And if you recognize this A, magnitude A, magnitude B, sine theta, this is actually A, magnitude of A cross B. This is by definition that we have seen earlier. And this actually give us the area of, parallelogram. Parallelogram. Why this term so difficult to pronounce, yeah? Parallelogram. So the area of parallelogram. So if you put there, so I can put parallelogram O Q R prime Q R Q O Q R and S. That parallelogram. Okay. Now to prove this, it's not difficult. And if you cut this into half, you just look at those. We have this parallelogram. Let me sketch again. We have vector B there. We have vector A here. Okay. So, and we have this parallelogram. Okay, this is vector A. This is vector B. If you cut this into half, that. So what can you see? This part here, this area and this area, because we cut it into half. Alright. So basically this area is half of the parallelogram, the area of the parallelogram. So what we can have from there, this is basically the area of the triangular, this at angle theta. So therefore So we have the area of the triangle formed by vector AB formed by vectors A and B is given as half of A cross B. Okay, now to prove this part, this is not difficult to prove. As I mentioned earlier just now, that if you look at this diagram carefully, the parallelogram, I think I use another paper to make it clear for you. From those parallelogram, let me sketch again. So we have vector A here, vector B is here. So we have the parallelogram that, and we put it a little bit longer here. This is 0, we have Q, we have R, we have R prime here, we have S here, this is angle theta, and then we have the height that is given by vector B, magnitude of B, sine theta. Okay, now, so what we can find from this diagram is that the area of those parallelogram O, Q, R, S is basically the same as the area of those rectangle. Okay, so we have Q, R, I put it, this is Q prime, so R, Q, R, put it Q, Q prime, Q, Q prime, R, and R prime. Okay, so from there we just need to show that Q, Q prime, this is B sine theta. R, R prime, Q, Q prime, or times this thing. Yeah, so this is, we need to find the length given as Q, Q prime, Q prime Q times QR. Okay, because the area of the rectangle, and QR, this QR here, basically the length of vector A, which is magnitude of vector A. So those times magnitude of vector A, and that gives us, that I have shown you, that A, B sine theta. Okay, so that's the area, the application of cross product. You need to know those things and differentiate how to show between parallel vectors and rectangular vectors. Okay, so let me give you example. Find a vector perpendicular. Yeah, a simple problem. Find a vector perpendicular to plane that passes through points. Yeah, I hope you can read this. Find a vector perpendicular to plane that passes through the points. Okay, so we have P 1, 4, 6, Q -2, 5, -1, and R 1, -1, and 1. Okay, so the easiest way to do this thing, let me show you how can we visualize this and how to find. It's easy, but if you cannot visualize this, so you might possible for you cannot answer this question. Yeah, the thing is easy, because now this point 3 points here are on the plane. So you can sketch the plane. So let's say this is our plane. Okay, then you put those 3 points. You can say this is point P, this is point Q, this is point PQR, anywhere there. Okay, from these 3 points, you are given those 3 points. Of course, we can form a vector PQ. You can form a vector PQ. You can form a vector PR. So having obtained these 2 vectors, we can just cross these 2 vectors. We can find the vector that perpendicular to that. So if you can also choose Q, P, QR. You multiply this, you got vector perpendicular to that. You can also use RQ, RP, you got a vector perpendicular to that. Of course, these 3 vectors that you obtain using different points of reference that give you different vector, but they are still perpendicular. To show those vector perpendicular, you can use again dot product that equal to 0. Okay, so I hope you can understand those things. So let's try this thing. So we can find, let's call, I use a P as a reference point, then P, Q, PR. So we have a vector, that vector. So let's call this vector what? Let's call this vector A, for example. We name it A. You can name it any name you want. So I put name A. So vector A, you can find as P, PR cross P, Q. Okay, if you put PQ cross PR, it should point out to the negative part. So but that doesn't matter, because what we want to find not the direction of that vector, but we want to find the vector that perpendicular to that plane. Right, perpendicular to the plane. Doesn't matter direction to upward or downwards. So you can always let's say PR times PQ or PQ times PR. Of course, if you PR times PQ, you got negative of PQ times PR, but still correct. And if you use as I mentioned earlier, if you use Q as a reference point, you got different vector. If you use as R as a reference point, you got the different vector. Okay, from there you can we can just solve this. Our PR, yeah, PR, I think you know this. This is 0, minus 1, minus 4, this is minus 5, 1 minus this is minus 5, cross our PQ, minus 2, minus 1, minus 3, 5 minus 4, you got 1, minus 1, minus 6, so minus 7. Okay, and then you can just perform. So what we want to find? We will find the vector perpendicular to the plane. Okay, so just perform that product. Okay, so how to perform that product? Apply this. Okay, you can use the formula that we defined earlier, or you can simply use the magnitude of the determinant of a matrix. Yeah, you can use the determinant of the matrix. So we have ijk, we have minus 0, minus 5, minus 5 here, and then we have minus 3, 1, minus 7. You can solve this thing. Okay, so I just leave it this part to you. And of course we can extend a little bit with those points. Let's say I can say find the area of the parallelogram formed by PQ, vector PQ and PR. Yeah? The other vector, other question from this you can have like find the area of the parallelogram formed by vectors. Hope you cannot see that. Vectors PQ, PR, or PR, PQ, doesn't matter. P, PR, PQ. Okay? And another one, find the area of the triangle formed by vectors PQ, PR, PQ. Okay, so for this you just need to find what is cross product, the magnitude of for those area of the parallelogram. This is the magnitude of PR times PQ. Yeah, you already have what is the vector PQPR. You have this from here, all right, and then having obtained those values, then the area of the triangle just half of that. Yeah, half of that. So I think I need to stop here for this video. Okay, so what I have covered in this video, that the continuation of the cross product and the parallel vectors, the important theorem on the cross product, and some application of the cross product, especially in finding the area of parallelogram and area of the triangular. So for the next video I will talk on the properties of the cross product and so on. For the I think for the time being I stop here. Thank you. Bye bye.